Today we want to look at how we can determine the period and the frequency using the principles of simple harmonic motion of a mass loaded vertical spring. We understand what a Hooke's law says, and Hooke's law states that for an elastic material, the force applied on the objects or that material is proportional to its extension or displacement, provided the elastic limit is not exceeded. So here we're talking about the mass loaded vertical spring, which is elastic in nature. So by the time you suspend the mass and displace it, it will oscillate. It will perform simple harmonic motion. So when you look at these three diagrams, diagram A, diagram B, and diagram C, in this position A, it shows when the body is not yet displaced, when it is in its equilibrium position or mean position. Then diagram B shows that if it is displaced and the mass is up, the force, that restoring force, is acting downward. And at the position where the mass is down, the restoring force is acting upward. So looking at this, our interest here is to derive an expression to calculate period and frequency when this body is performing a simple harmonic motion. In the other class, we'll look at how we can determine the acceleration due to gravity in the case of a simple pendulum when the body performs a simple harmonic motion. So our interest here, or the emphasis here, will be on period frequency. So from the statement of Hooke's law, we know that F is equal to minus kx. This side, equation 1. We know force is the applied force, x is the extension, and k is the force constant. In this case, we have minus because of the restoring force. So from Newton's second law of motion, we also know that F is equal to ma. If this are equation 2, so by the time you relate equation 1 and 2, relating equations 1 and 2, we now have this. We now have ma is equal to minus kx. So if F is equal to this and F is equal to this, ma will be equal to minus kx. So if this is equation 3, and if you make A the subject, A now will be equal to minus kx all over m. And maybe these are 4. So but from we also know that F is equal to m omega square x. When we're talking about centripetal force, we use R, but here we use X because we're talking about displacement. So if this is equation 5, so by the time you now relate equation 1, relate equation 1 and 5, we now have minus k, we have kx equal to m omega square x. So k will take care of k here, and we have omega square to be equal to omega squared to be equal to k all over m. So if these are equation 6, but we know that recall that period is equal to 2 pi f. Is that right? No, angular uh, velocity is given as the angular frequency is given as 2 pi all over t. Angular frequency is given as 2 pi all over t. If this is 7, so the time you substitute equation 7 into 6, we now have 2 pi all over t squared equal to k all over m. So our interest here is to make t the subject. And the only way we can achieve that, that is, let's bring it up, 2 pi all over t squared equal to k all over m, is to square both sides. Square both sides of the equation. So if you square the sides, we now have 2 pi all over t equal to k all over m all squared. As we square both sides. So in this case, we now have, some will be asking, how? Okay, let's do it this way. We can write this expression as square root of 2 pi all over t equal to k all over m. So if you square both sides, means you have squared this. So square root of 2 pi over t times square root of 2 pi over t is 2 pi over t. So that's what will be. And in this case, we now have to square both sides, you have 2 pi over t equal to k all over m squared, which we can represent as 2 pi over t equal to square root of k all over m, which when you break it down, we have 2 pi over t is equal to square root of k all over square root of m. We can write it this way. So by the time you cross multiply, we have t square root of k equal to 2 pi square root of m. So doing this will make t the subject. T now will be equal to 2 pi square root of m all over square root of k, which you can write as t is equal to 2 pi square root of m all over k. So this is our desired equation to calculate period of a loaded spiral spring. So what of frequency? Recall that frequency t is equal to 1 all over f, and f is equal to 1 all over t. We know this. So by the time you evaluate this, frequency now becomes f equal to 1 all over 2 pi square root of m all over k. So we can write this as 1 all over 2 pi square root of m all over square root of k, which we can write as 1 times square root of k all over 2 pi square root of m. So doing this, we can say that f is equal to 1 or root k all over 2 pi root m, which we can write as 1 over 2 pi square root of k all over m. Therefore, f is equal to 1 all over 2 pi square root of k all over m. This is for frequency. So, we have achieved our aim. One will ask, why derive this? Because I told you, for you to understand physics, you should know how these equations are derived. And with that, you'll be able to apply this equation in solving your problem. So we have a problem here. A spring was mounted horizontally with its left end held and pulled towards the origin. A force of 6 newtons causes a displacement of 0.03 meters. The spring balance was then replaced with a mass of 0.5 kg and was displaced for 0.02 meters. Find the force constant, and B, the angular frequency, frequency, and the period of the. So in this, I'm going to give you something to do. I will give you hints on how to solve this solution. For the first one, force constant, F is equal to minus kx, and k is equal to minus f all over x. Use this to where force is given, the displacement is given. And then for the B part of it, find the angular frequency. Angular frequency is equal to 2 pi f. Is that right? But what is omega? Omega is not given. Is that right? So omega is square root of k all over m. So by the time you find this, you can calculate your angular frequency. And then your frequency is f is equal to 1 all over t. Is that right? Which you can, in this case, you can say that's 1 over t, and then the period t is equal to 1 all over f. So if you do this, let me know